Okay, so our goal for today is to review for this exam, and I'm going to try to structure this sort of similar to how I would want you to be studying at home. All right, so what we're going to do first is we're going to go down to our exam 3 module here. In addition to your practice assignments, there's this reagent bank here, all right? And what this is a bank of all of our reagents that we used in this particular unit. And I want everybody to take a minute and attempt, without looking in your notes, to go through and classify these as either being reactions of alkenes, alkynes, or both. All right, so see if we can't just divide up all of our reagents here as for what we use for what, right? We're going to go through and first just pick what is our substrate. Is it an alkene or an alkyne, or does it work for both? And then we'll work on actually practicing each one of these, all right? But take a second and try to divide this up first, all right? You can do it in your notebook. I also handed out these blank pieces of paper, whatever you want, all right? But again, the goal being without looking in our notes, let's try to do as much from memory as we can here. Oh, perfect. All right. All right, and when you're done, you're going to pick 4 alkene reactions. You're going to use this particular alkene as your substrate and practice 4 of those reactions. And you're going to pick 4 alkyne reactions and do the same thing with this alkyne. All right, I'm going to kind of quietly fill in up here these different categories. I'm just going to kind of color code. So I'm going to do alkenes in red, alkynes in green, and both in blue. Yeah, so the ozonolysis thing, I did look into it. So this is the same that you would do for both, that same first step. Strictly speaking, there's like a second, what they call workup step that you would need to get for your product. For alkenes, you would use something like dimethyl sulfide, whereas alkynes, you need to use an aqueous workup. This is the important step, and that's the same for both of them. So this is what I'm going to put on your reagent list here. All right, but yes, ozonolysis for both alkenes and alkynes, that happens under the same conditions.
Professor, are you recording this section?
I am, yeah.
You changed the reagent list, right? Because earlier.
There were a few that were like not combined. So for example, this one here, there were the two steps listed separately, and I just put them together since that's what I want you to recognize is what they do together. Yeah, so that would have been a third step. Rather, I just listed it here. Rather than having them all separated, I put them together basically. So yes, I did change it ever so slightly. I tried to simplify it.
Professor,
Yeah.
don't you use the X2 over KOH to make an alkene into an alkyne?
Yes. Yes, you do. Good call. Right chapter, wrong substrate. Yep, good call. This would have been how you'd create an alkyne, not a substrate of an alkyne. All right, so take a few seconds again. You're going to pick 4 of these reactions to do for an alkene, and then 4 to do for an alkyne, and then we're going to go through a few of them. Yeah.
Alkynes have to be linear, right?
Specifically, whatever, like these 4 atoms in my implied hydrogen, that's the part that has to be linear. So your triple bond and then the bonds coming off of it need to be linear. Yeah, and remember I said at the beginning, I even straight up told you, I'm going to have you draw an alkyne on your exam and you will get points off if you don't draw it in that linear geometry. All right, your homework system lets you get away with it, but when you're drawing them on your exam, you need to be good about making sure you have that linear geometry.
Would you choose 4 random?
Yeah. All right, so we'll get to our reaction practice here in a second, our alkene and our alkyne. But again, sort of my goal is to kind of do this study session in a way that I would sort of approach if I was studying this material. And step one, I'm going to pull up this reagent sheet, and I want to make sure that I have like some understanding of what I'm looking at here. So for example, if I see a reaction and I'm like, oh crap, what is that one there? I'm immediately going to go make sure that I recognize what these reagents do, right? Being able to sight recognize. We don't have to have them memorized. They'll be given to us on the exam, but we do need to know what they do. So a very simple thing to sort of test myself on whether or not I know my reagents is to divide them up based on their substrates here, right? What do I use alkenes for? What do you use alkynes for? And what can we do with both? Similarly, I can go through and let's instead take a second. We have a few reactions that fall under the umbrella of a hydrogenation reaction, as well as reactions that fall under the umbrella of hydration reactions, and a few that form diols. All right, so everybody take a second and see if you can categorize which one of your reagents would you put under this umbrella of hydrogenation reagents, hydration reagents, or diol formation reagents. All right, which one of these are our hydrogenation reagents? Somebody give me one. So Lindlar's one for alkenes, rather to create alkenes from alkynes, specifically with that Z stereochemistry. Which one does my E stereochemistry? My sodium and ammonia. And then what's the one that works for both, reducing them both to alkanes? Our palladium H2. Okay. What about hydration reactions? Our simplest one that we have our mechanism for is our dilute sulfuric acid. That's our hydration reaction of alkenes. We had another one, these oxymercuration reactions. These both here with that mercury, these are both hydrations. One of them, the mercury acetate, mercuric acetate, is for alkenes. Mercury sulfate is for alkynes, but both hydration reactions. These were both the Markovnikov hydration reactions. And which one was the anti-Markovnikov? The boronations with our boron here. Again, slightly different list for our alkenes, which use borane, versus our alkynes, which have that those two alkyl groups, those two R groups on the boron. All right, but nonetheless, all these would be our hydration reactions. All right, again, we could even go through just kind of studying on this here, which one of these are Markovnikov and which ones are anti-Markovnikov. Everybody take a second. I think I kind of gave it away, but the mercury ones are our Markovnikov, as well as our acid catalyzed with that carbocation intermediate is Markovnikov. The hydroboronation reactions are the anti-Markovnikov hydration reactions. All right, and then what about my diols?
The
Yeah, so we have our osmium. That would be our syn addition. All right, the other ones, our anti-additions, are when we form these epoxides first. And we can either, both of these would give you the exact same product. We could either use that peroxy acid, or we could do a halohydrin treated with base to get an epoxide. And then that last acid step is where we get our diol. All right, and similarly to before, we can note that this one is our syn addition, and these two are our anti-addition. All right, so again, just kind of going through just our reagent list and trying to study that reagent list, make sure that these look familiar, right? These should, in an ideal world, you look and you're like, oh, I know exactly what that reaction's used for. That's the goal, right? That's where we're trying to get to.
Is that what the under basic and under acidic conditions is one of those stuff? Or is it something else?
That was actually our tautomerization that we were talking about the conditions for. So it was the conditions are specific to a mechanism and what your intermediates are allowed to be in that mechanism. All right, so let's go ahead. I'm just going to clear this off here. All right, we had to pick 4 reactions for alkenes. Regardless of whether you picked it or not, what's one that we should do here? What's one that you would like to see because maybe you don't recognize it?
The halohydrin?
Our halohydrin. All right, so that's when we have some halogen. Let's just go to bromine and water. Okay, if you had not already done this one as an example, everybody take a second and fill in what our product would be here. All right, halohydrin is when we have a alcohol group and a bromine in the same molecule. All right, here we have these 2 carbons. One of them is more substituted than the other, and these halohydrin reactions are specific about which carbon's going to get the halogen and which carbon's going to get the OH group. We said that these reactions were Markovnikov, specifically for that hydroxyl group. So the hydroxyl group goes on the more substituted carbon. The bromine goes on the less substituted carbon. I specifically chose this alkene to start out with because we're not going to get any stereospecific products. This is an anti-addition here, but I don't have 2 stereo centers formed. I only have 1. This one's not a stereo center, so I don't have to worry about my dashes and wedges with my product. We'll sort of get there. What's another one that we should take a look at? Alkene reactions. Give me one. The diol. All right, let's go for, in this case, it wouldn't matter which one I chose, actually, because we don't have our stereospecificity. But nonetheless, we'll use that peroxy acid followed by our dilute acid. All right, and as the name implies, we're going to get a diol, where we have a hydroxyl group on one carbon and a hydroxyl group on the other carbon.
So this could have also been the 2 halogens in water with NaOH?
Correct.
Okay.
That would have given you the same exact product. Actually, so would the osmium in this case, just because there aren't stereo centers.
Sure, yeah.
What's another one?
Oh, the only reason we didn't use the dash and wedge is because there's only one stereo.
Correct. Yep. Again, I specifically chose this alkene because none of our reactions will give us a stereospecific product. There are already 2 hydrogens on this carbon on the end here, so it can't possibly be a stereo center.
The acid catalyzed hydration?
Sure. So acid catalyzed hydration. All right, and then we're also going to do that ozonolysis reaction as well. So everybody take a second and fill in these 2 if you have not already. Yeah. All right, so yeah, we're going to do an acid-catalyzed hydration and a hydroboronation reaction. Both of these are hydration reactions, but they differ in their regioselectivity. For acid-catalyzed, where am I going to put the hydroxyl group? On the red carbon or the blue carbon?
Red.
This is our Markovnikov, our hydroboronation reaction, boron giving us that anti-Markovnikov product. All right, so I get a butanol in each case. This is a 1-butanol versus a 2-butanol. Okay. The ozonolysis reactions. All right, I can say in DCM, very, very cold conditions. These are our reactions that were not these addition reactions. These were these oxidative cleavage reactions. So this reaction is actually going to chop this molecule at that carbon-carbon double bond. So I'm now going to get one fragment with a carbonyl group. That would be 3 carbons long. I'm also going to get a second fragment here with my blue carbon. A formaldehyde fragment here, my carbon-oxygen double bond. All right, so again, stuff that you can do on your own to practice. I just put down a random alkene. I went to my reagent list here and I picked a bunch of random reactions that correspond to alkenes, and I figured out what my product would be. All right, so let's play the same game with our alkynes now. Everybody take a second to finish up your reaction wheel for our alkynes. I'm going to put down a few random ones as well that we'll work through. All right. What's up?
For the alkynes, there's not that many mechanisms we're supposed to know, right?
There's almost none for the alkynes, yeah. The exception being the half of our tautomerization, and we also did have a mechanism for when we treat a terminal alkyne with a base, just to deprotonate it, that acid-base step, and then that nucleophile attacking our alkyl halide. That one we did see a mechanism for. And your study guide does make it clear which reactions we should know mechanisms for and which one we shouldn't know mechanisms for. All right, and actually let's do these oxymercuration reactions next to our hydroboronation reaction because they're very similar. All right, so we get that addition product. But remember, those enols are unstable, so they will tautomerize. So I don't actually get an enol product. I get a aldehyde or ketone. All right, again, we have these two carbons with these different degrees of substitution. For a oxymercuration, which one is that? Markovnikov or anti-Markovnikov? Markovnikov. So that one's going to have that carbonyl group on that more substituted carbon, giving me a ketone. Whoops. All right. If instead we did our hydroboronation reaction, our enol would tautomerize into an aldehyde. Giving us our hydration product. All right, our halogenation and our hydrohalogenation. These were reactions of both alkenes and alkynes. All right, so we could either add one equivalent of our reagent and just get one addition, or we could add two equivalents and get two additions. If we just add one equivalent, we break only one of those carbon-carbon pi bonds, leaving us with an alkene product. All right. And just like with alkenes, alkynes will react in a Markovnikov fashion with those hydroboronation reactions. So our bromine is going to go on that more substituted carbon. All right. If instead we did two equivalents, then we would break both our carbon-carbon pi bonds, and we would get two additions of our reagent, in this case a halogenation. So I get two chlorines on each of my carbons. No stereochemistry. Yep, same. Since we chose a terminal, so that made our lives a little easier with our stereochemistry. Okay, cool. So now, in order to practice, we're all going to grab a new sheet here. All right, and everybody's going to take a second and draw 3 alkenes here. All right, and space them out pretty nicely on the page here. So one at the top, one in the middle, one at the bottom. All right, you're going to draw 3 different alkenes. All right, I'm going to put some restrictions on it here. The first one should be a terminal alkene with at least one branch point. The second one should be an internal alkene that has stereochemistry. And the last one should be a tetra-substituted alkene. All right, so everybody's going to draw one at the top, one in the middle, one at the bottom. 4 alkenes here. Uh-huh. It's not wrong. It looks a little weird because you've bisected that angle right there, whereas if it was a tetrahedral, the 2 bonds would be pointed in the same direction. Since it isn't a stereocenter, though, you would have gotten away with it, since there's no dashes and wedges. If there were, you cannot put them on opposite sides like that, or it's incorrect. All right, and what we're going to do in a minute is you're going to take your paper and you're going to pass it to the person on the left, And they're going to name those alkenes. All right, so once you're done drawing your alkenes, you're going to pass it to the person to your left, and that person is going to name those 3 alkenes.
Quaternary? No, the quaternary. That's the one where it has 3 neighbors, 3 carbon neighbors, or 4 carbon neighbors.
Well, yeah, 2 for each side of your double bond. So you'd have, like, the smallest possible tetrasubstituted would be this one here. And then we could add more carbons on there. Oh my God, that's so ugly. All right, so pass it, if you have not already, to the person to your left. Should all go in a circle here.
On both sides, they have to have 4 carbons.
So a tetrasubstituted means that these 2 carbons here have 1, 2, 3, 4 neighbors. That would be a tetrasubstituted alkene. I guess try would have been fine too. But. All right, make sure to include the stereochemistry when relevant.
gave me 3 penties, bro. What the fuck? He gave me 3 with different substituents. Or try math.
6 carbons. You actually like that?
I'm not interested. You gave me this year.
Methyl. Yeah, sure. Okay. Yeah.
We're in the gray.
Yeah. 50 miles. Yeah. Type shit. You just continuously pass around.
No, so then what we're going to do is now you're going to pick 6 reactions of alkenes, and you're going to pick put 2 reactions on the first one, 2 reactions on the second one, 2 reactions on the third one, and pass it back to the original person. All right, so pick reactions from our reagent bank here, right? 2 reactions for each alkene, 6 different reactions, 2 for each alkene. Pass them back.
I didn't make mine. I didn't even know what I was doing. I was drawing lines. No, that's not why. Yeah. So I'm gonna give Sam the hardest.
You don't know which ones apply to which? That was our first exercise of the day. Take your reagent bank and split them up into which reacts with what. That's like a great first way to study.
What's your favorite reaction?
Probably the hydrohalogenation reaction, just because we got a full mechanism for it and everything. Carbocation intermediates are pretty cool.
It was just any reaction, right?
Yeah, so 2 for each alkene. Yep.
2.
So 6 total, 2 for each alkene.
Multi-step synthesis. You got this. Go. Retrosynthesis.
I think they gave one of them boys.
Not following directions. What's up? What? Syn addition diols.
What is the RC?
That's an anti-addition diol.
So actually,
Peroxy acid is what they're called. So you were close, yeah.
So we're gonna do the thing, like, should we know, like, how to go from the yellow hydrogen to the oxide to the diol?
That was one of our mechanisms, yep. The exam can't be all mechanisms, but that is one that we know, yes.
How many mechanisms of questions would it be then?
Like hypothetically.
I don't know.
Like, what's your favorite
A million.
mechanism that like you've ever seen?
You really like that acid catalyzed hydration. That was on the homework like a bunch.
Yeah, that's a good one. There's one in the second semester that's pretty cool that I like a lot. Forming imines from aldehydes and ketones. Yeah, not amines, but imines. We'll get there. We'll get there. All right, so once you get your reactions, pass it back to the original drawer, and they're going to fill in those products.
I'm not getting it.
I'm sorry.
Because I'm failing this class.
You don't have to do this. Yeah, you don't have to do your reactions. I promise.
I gave you the last one's pretty not too bad.
Too bad. I don't know the stereochemistry of these.
That's part of it.
No, that one didn't have stereochemistry because it has two of the same substituents. It has two ethyls attached to it.
Wait, what is it?
Yeah. It's true.
I drew this?
I knew this.
I didn't know I drew this.
The whole bottom. I wasn't thinking that far. He said write down reactions. That's what I did.
I did myself.
Whatever you need to do, space-wise.
I did myself dirty.
Thank you, Tracy. Really worked this out for me. Oh, I know this one actually. I take it back. I don't tell you.
Yes.
The racemic mixture. That's what it is. Wait.
I don't know. I think some stereochemistry.
Everybody should have a terminal alkenes. They shouldn't have to worry about stereochemistry for that
I
first
did one of
one.
them. But I don't know what else.
I tell you, it's great. You gave me 4? Oh, damn. Okay, okay. Hell yeah. No,
Wait.
I got it.
Make it double O. I don't know. Why did they draw that? Did we just do it? We did just do it. It's double O. I have to retake. So yes. Oh wait, no, this one is.
Sorry, you gave me X2 against him challenge.
Pick your favorite.
I'm gonna pick my favorite. I got
Try
it.
X. Chrysippus?
What up?
What's your favorite halogen?
Bromine, by far. I
Really?
have no idea why, but yes. Fluorine just doesn't really count.
Is that kind of
That's a pretty cool one too, but.
all of the practice problems have
Bromine works better as like a leading group and a nucleophile, so it's actually like it's kind of defaulted to as well. You will see it more than all the other halogens. I think iodine works great. It must be expensive or something, because it's just not quite as commonly used. That's how. So they're both very similar. So we got 2 mercuries. Look, we got 2 mercuries, and honestly, if you mixed them up, I would give you a hell of a lot of partial credit because they both are Markovnikov, and they're both hydration reactions. But yes, the acetate is for alkenes, the sulfate is for alkynes.
And then for hydrations, there's no hydration. There's no shifts on oxygenation.
Nope. Compared to acid catalyzed is the only one where you have issues.
Wait. The sodium and ammonia mix an alk, right? I'm pretty sure I caught that.
Correct. Yep.
How do you drop that? Now, how are we checking this?
I'll check it.
Well, that's not what I Usually you don't. Because I haven't written anything yet. So, 2 check questions. What does X2 do?
Okay.
Is that syn addition or anti-addition? Or is it anything addition?
X2
Or
would be something like
there's no
bromine.
stereochemistry because there's two hydrogens, there's a neutral matter.
Yes, except for no. There is stereochemistry. There's not two hydrogens. There's only one hydrogen.
Four. So that's so it's syn addition, right?
It's an anti. Let's go for it. Yeah, yeah, that's your anti-addition.
How would you draw this as an alkyne? Because it has a.
You can't.
So.
Well, how am I supposed to?
Did you try to do the turn it into an alkyne reaction?
No, he just tried to
Yeah,
make
so
me
that would be
brown.
that would be no reaction then basically.
Anthony, is it the X?
You picked
Is it the X one?
I put a
This one.
constituent off a double bond.
Which you can do, but you just couldn't turn it into an alkyne for exactly that reason that you're thinking
What is
about,
no
right?
reaction on that? I didn't know. Now we know.
Now we know. Well,
Yeah,
I
because
say
there's
that the
no
first step would occur. There would be no second step. That would
What does sodium and ammonia do? I literally taught this.
not
It's,
dehydration. Not no elimination
Mixed
step.
into an
Okay.
alkene.
Oh, so that's not.
Mixed into an alkene. NaNH3 mixed into an alkene.
No.
Okay.
Yeah, so then you do that.
It is a syn addition. Yeah. So those two methyl groups are going to be pointing on the same side.
And so how do you draw it like with that? You should draw it straight.
Yeah. That would be.
Because this doesn't have stereospecificity.
Correct.
Oh, no,
Carbocation
we're making
alleviates
it
no
to-
stereospecificity.
Yeah, it's alkene alkyne.
You can't add any NH3 to that.
So if there's water in there, one of them's going to be a bromine, the other one's going to
You
be.
can't add any
If it was
NH3
just
to that.
bromine, then this would be.
That's for an alkyne.
Alright, but with the H2O, that's the
Oh, that was
hydrogen.
you. That was your fault.
Or halohydrogen.
It's an alkyne to an alkene, right?
Yeah, you can't do that.
Same thing up here.
That's a leak.
Same idea. Yep.
That could be an NH2.
Oh, okay, okay. Well, right. Cannot be possible.
D&E does not exist.
Because this carbon
So
is
did I actually?
That was a test, right? There you go. Good one, boss. What does the RX go into?
That's an electrophile.
Right. It strips the sodium.
So what is
strips the
RX?
hydrogen,
It strips the hydrogen, yep.
And then it's gonna make the carbon an electrophile. And then the
No. If it strips the hydrogen,
no nucleophile.
it's going to have a negative
It
charge.
has too many electrons.
It's got a lot of electron density, yep.
There you go.
So this thing here is what you get, right?
Wait.
If I,
Do you use for alkenes though, or no?
no.
Oh.
Oh, yeah. I guess, true. This, no, you can't use on alkenes. It's got to be a terminal alkyne.
You're just testing me, huh? This is all a test.
You might not be able to. If you got too many carbons, if you are tri or tetrasubstituted, you could not turn it into this reaction is exactly what it says. You try to put a triple bond there and all of a sudden carbons would have too many bonds. So this one wouldn't work. You can do that one.
What does epoxide do?
You make an epoxide, and then when you treat it with acid, it turns into a diol. So this thing here is a way to make a diol. Yep. And then you got to remember if it's the syn or the anti-addition diol.
Because you can make an alkyne out of that.
Syn addition.
Because when you
Nope.
make that triple bond, you have 3 plus that equals 4. For this one, if I made a triple bond, this would have, like this carbon, for
Give me a
example, would have
second.
1, 2, 3, 4, 5. This one,
For which reaction? Where's your? Yes,
this
correct.
carbon,
Yep.
for example,
Yep.
would have 1, 2, 3, 4, 5. You can't have 5 bonds on a carbon.
Yep.
That's why this doesn't, because you can't make that out.
Yep.
That one could. Yeah, that one could.
Yeah.
Correct. Because of what you were saying about neither being more substituted than the other. Yeah. Oh yeah. Okay.
And then this one, since it only has one chiral center, you don't have to show
Correct.
wedges or lines.
Yep.
So it'd just be that.
Yep. And then, like, if it wasn't, though, you would want to note that would be a syn addition for that.
Should I be drawing the two different possibilities?
Correct. The methyls would mess you up. All right, and again, kind of just my point here. How did we do this all we did was we drew random freaking alkenes, and then we picked reactions from our reagent bank and tried to work with that alkene to figure out what our product would be. So again, a great way, you could do this by yourself, but it's a great thing to do with a partner as well, where you're gonna draw it out, try to stump them, right? Something that's gonna be hard to name, to pass it over, all right? And then yes, pick some reactions and then do what your reaction, your product would be for those reactions. We're gonna play the same game one more time. Everybody's gonna flip over their paper. You're gonna give me one terminal alkyne and one internal alkyne. All right, now we're gonna pass them to the right, and your neighbor's gonna try to name them, pick some reactions, and pass it back.
Am I supposed to know what that means?
Ideally, yes.
Because I don't.
What would a terminal, okay, I believe in you. You can figure this out. An internal alkyne.
Inside?
Yeah, when your triple bond is in the middle, a terminal means it's on the end, on a terminus.
When did we learn that?
Use the word clues.
Yeah, well, terminal, I thought it was thinking of terminal illness.
Which is the end of life illness, right? So,
Alright, well, I didn't think about it.
Or should we send out on the last one? Because that OH would make this carbon have 5 bonds.
well, then this is just our drawings, correctly, right? That
Where? This carbon right here?
Oh, yeah, you're right.
4, 5.
You're right, that's my bad.
Well, there would be a curve.
No.
What is this?
Wait, you're not
6 bonds.
I'm just giving Sebastian.
Okay. I was like, don't you
There's
do
going to be the
this
same
every
5 extra
single
points
one?
as there always is.
He was trying to stop me.
Wait, did you pass it?
For which one?
She gave me a carbon with 6 bonds on it.
Yeah, that's one way to do it.
To the right or to the left?
Not just 5 bonds, but 6 bonds. That's
That's a drawing?
a lot.
I have to practice this before it leaves my mind. I have about 2 minutes.
And then I need to give you reactions after I see them.
Okay. This one was really good. You don't have to make it. We don't quite know how to do that. It wouldn't be a parent chain, and this would be a cyclohexyl group instead of the parent chain of the molecule. And so yeah,
Name
actually,
of parents again?
Wait, okay, so I just named them. And I put it back in the alternate.
Oh, well then get rid of the other, get rid of that end part.
I feel like I'm gonna do that.
what up?
So we name, give them reactants, and then you know.
Correct, yeah.
Okay.
Yeah.
I got lost in the sauce.
I'll give you mine. Okay, alright.
I'm gonna name it
You got, you have.
methyl what? What is it? 6 methyl.
You do have to put the 1 because if it was 2, it would, 2 butine as a different molecule. Yeah. So propine is one of the ones where you actually wouldn't have to include the 1. Because if you moved your triple bond over, you would just count in the other direction. So you could just say propine. That's a pretty minimal mistake.
Why do we not see like
I don't know. We don't really see them quite as often, though. I've actually been sort of lobbying to get a few in here just so I could do like IR with them and stuff like that. No. And I will also say that we tried to make one year using our method and it didn't work at all. So I don't really know. Maybe they're a little bit harder. Maybe our conditions weren't right. We did just kind of wing it. We tried to do our reaction to make alkynes. One semester, somebody has the project that you guys are working on. Somebody tried to make some alkynes, and it didn't work very well.
Right, we're giving them reactions and passing it.
Correct, yep. Pick 2 reactions from our list here and pass them back. 2 for each.
Oh, have fun with this.
So for the test, we should know properties, alkanes, and alkynes. Should know reaction mechanisms. Should know these reactions. And nomenclature.
And nomenclature. Yep.
That's it?
Yep.
You're not going to throw any other curveballs? No?
That's it.
Okay.
Those are the big ones.
I actually don't know if you can do this. Figure it out. Let me know.
Is the lithium one not in here?
To be fair.
The lithium or sodium, so I have sodium on here instead.
Oh, sodium.
But we have to remember that it's
Or ammonium. Sodium
Uh,
and ammonium.
This is going to be our reagent bank here. This is what I posted on the exam module, so this is what I'm going to stick to.
Gotcha. Thank you.
I made that so easy for you. I didn't even think.
Let me know.
No, you didn't get it. You got it. Made it way too easy.
There wasn't even any
I was just focused on drawing the right thing, and I still failed at that. H2 thing.
Oh, is this right? I just dropped it. I don't know what they're supposed to be. Did you Thank you.
Methyl's with amphetamine. What's an amphetamine? There definitely is a methyl. Oh, on the nitrogen?
There we go.
I'm trying to remember what it is. It's like a benzene ring. I don't know how many carbons. I don't remember how many carbons it is, but definitely the difference between amphetamine and methamphetamine is just the methyl group on the nitrogen.
Wait, is it methyl group? That's why it's methyl.
That's why it's methamphetamine, as opposed to 2 hydrogens. That's amphetamine. That's methamphetamine. Which is an instructive thing because it's a methyl group, so
Yeah, we should just like go through it, see what happens.
Anthony.
which makes it what? More or less polar?
Introductional learning.
Yeah, seriously, more or less polar if I took a methyl group, or if I exchanged a hydrogen for a methyl group.
Less polar.
Less polar, which is why it's better at passing through the blood-brain barrier and making it more dangerous than regular amphetamine.
Anthony, you see Breaking Bad, right?
Yeah.
Science. Science.
For all kinds?
I give up on brains.
I mean, if you want to make it hard, you can make the RX stuff.
HG as a forming.
The
Or wait.
or dials over it.
Oh, I see.
You could give me
Wait.
Alright, makes an OH more common.
Oh, that'll fully reduce
More problems off.
no double bond at the end. Whereas this one would give you, actually this one
I don't know
would
which
give you
one's stale chemistry or which
but this is the one, this and the Lindler give you an
There's no
alkene
Lindler,
product.
it's
This
checked.
gives you an alkene product.
And then since that's the concept,
80%
when I get it, like if I
great.
study what everything should ask, then when I
Do we have to make the different products if there's two?
Yeah.
Or will there be like a multi-step synthesis?
They're definitely going to be multi-step synthesis. Yep.
What? Just
I thought I misheard you, but you did say group crying sesh? Okay. Sit in the pain.
Bro, what? That's not possible.
You gotta relish it.
Okay. So just real quick, is there any one of these that we want to see worked out here?
That long one.
All of them.
Which long one? This one?
Oh wait, you can't do that for this now.
Will we have the anti-addition diol like full synthesis? Like, will we have to know that?
I mean, for a practical matter, if that was your mechanism question, that could be like the only mechanism question that I could put on there because it's so long. But yes, we do know the mechanism for that.
Oh,
That is
So
listed. Hypothetically, it could be on the exam, absolutely.
Can you do that one, please?
Sure.
What?
All right.
Your paper first. I don't know which one's mine or yours. This one's mine.
Cool. All right. So, step one, we're going to do a hydrohalogenation reaction. So, everybody take a second and give me my product here. Not a hydrohalogenation reaction, I'm sorry. A halohydrin formation. There it is.
So it's in water?
It's in water, yeah, sorry. This is a halohydrin formation. You're going to get a halogenate, you're going to halogenate one carbon and then put a hydroxyl group on the other carbon.
Where are we doing the mechanism right now?
We're going to do the mechanism, yep. So step one, so let's say that we get this problem on the exam and we have to do a mechanism, all right? Step one is draw your product. You want to know like where you're going, right? That'll make it a little bit more clear in terms of your mechanism that you're going to do. So step one, I'm just going to make sure that I know what I'm trying to get to here, which again is that halohydrin. It's got a halogen on one and a hydroxyl group on the other. Remember we said that these were my Markovnikov to that hydroxyl group. So at least now I know what bonds I'm trying to form here, right? What bonds I need to break, what bonds I'm trying to form. All right, if we're going to do our mechanism, now I want to start thinking about nucleophiles and electrophiles, right? We want to be able to ideally look and say, all right, this is going to be my nucleophile and this is going to be my electrophile. Okay, our alkenes play the role of what? Nucleophiles or electrophiles? Are they electron rich or electron poor? They're electron rich because that carbon-carbon double bond. All right. These reactions here have that cyclic bromonium intermediate. All right, so our carbon forms a new bond with bromine, but then bromine fights back, forms a new bond with the other carbon. We get this cyclic bromonium ion intermediate. All right, we haven't used our water yet. So out of these two, water and this cyclic bromonium ion, what's my nucleophile and what's my electrophile? In this case, the electrophile should be pretty easy to spy. The cyclic, and what was it that gave it away about that that's an electrophile? That positive charge, right? So my water is going to be my nucleophile. And let's look carefully which carbon is my water going to attack, the red or the blue? The blue.
That's because the bromine, like the partial dipole thing, right?
Yeah, so basically this bond over here is weaker because that carbon's more substituted, so it can hold a partial positive charge on it. Easier than the other carbon.
Always there's a correct one you're supposed to go.
There is a correct one in this case, yep. All right, so now our triangle opens. We're almost there. We have our bromine in the proper place. We have our oxygen in the proper place. All right, but I'm not quite there yet. Why? Compared to my product, what's going to be on this oxygen? 2 hydrogens. And if it's got these 3 bonds here, it should have how many lone pairs? 1. And what should be its charge? Positive. All right, so we're going to have some base come along here to deprotonate. All right, and this I'm remembering I wanted to send an announcement out. You'll see this 2 ways, and so let's look. We have water floating around, and we have bromide ions floating around. All right. You will see certain textbooks that use this bromide as your base here to deprotonate that alcohol. But truthfully, if we're being good and we're thinking about it carefully, out of these 2 molecules here, which one is the stronger base? Water. Bromide here is a terrible base. That's why hydrobromic acid is such a ridiculously strong acid. So really our water here should be the one deprotonating. It's a pretty minor, I would give it to you on an exam if you use the bromide, as long as your electron pushing arrows and everything were correct. But if we want to be super correct, we want to think about what our stronger base is here. All right, so that was our first step, is creating our halohydrin. Okay, our second step is when we take that halohydrin, we put it in some basic solution, and we get this epoxide product, this carbon-oxygen 3-membered ring here. All right, what do we know about 3-membered rings? They're not very happy. These epoxides are very reactive. That's why this isn't our endpoint. This is, another checkpoint on our synthesis here. The other thing is, whenever I see something like potassium hydroxide, sodium hydroxide, the first thing I do is ignore the crap out of that metal, because that metal is never doing anything. It's a spectator ion. The thing that's really going to be involved in this reaction is this hydroxide ion. What's up?
Well, we need to know the mechanism to get to the epoxide.
This step, that's what we're going to do here. Yep. Yep. Because it's very straightforward. All right. Again, let's think about it here. What's going to be my nucleophile? What's going to be my electrophile? Looking at charges.
Your nucleophile is going to be the OH.
My hydroxide here. All right, and hydroxide being a good nucleophile, more specifically a good base, it's going to deprotonate that oxygen. All right, so everybody's going to take a second and draw me my intermediate here. It's actually just one more step. All right, so now my oxygen has that negative charge. All right, and this one here was this cool step in our mechanism where we have both our nucleophilic site and our electrophilic site in the exact same molecule here. All right, so this nucleophile and electrophile all built into this one intermediate. I want you to take a second and try to find your nucleophile, your electrophile, and you even have a leaving group there as well. All right, so identify your nucleophile, identify your electrophile, identify your leaving group, and then what do nucleophiles do to electrophiles? Attack. All right, my nucleophilic site. Where's my electron-rich nucleophilic site? The oxygen. And what's my electrophilic site? The carbon. And look again, right? We did where we're going here. What new bond are we trying to form between our oxygen and our carbon? So then what's the bromine doing? Leaving group. Right, so my nucleophile attacks my electrophile and kicks off that leaving group. All right. I'm just going to tell you straight up here, there was one more step here, of course, to get our diol, where we treat our epoxide with a dilute acid. All right, we are going to spend an entire chapter on epoxides next semester, and so I'm going to kick the reaction mechanism for this particular step until that next semester here. So whereas we should know our mechanism for halohydrin formation and for our epoxide formation here, I'm going to go ahead and just tell you, you don't have to worry about, we'll say no mechanism for this particular step. All right, we'll cross that bridge when we get to it next semester. Cool. Anything else? I guess we're out of time here. Yeah, how's that? All right, cool. If you guys have any last minute questions, please send me an email. Remember, there are those study assignments that you have posted as well. There's the reaction practice that you had to do, but there's yet another one, another copy of that same assignment posted for practice that you can do, do it with the friends. You get a bunch of different reactions. You both can do it next to each other and check each other's work, all that jazz. Cool? Yeah.
Did you give us the full mechanism before?
I did give you that last step.
Okay, but we don't need to know at this time.
No, again, we are going to address epoxides next what am I thinking? Semester, there it is. And for the particular example we did, there was nothing too terribly complicated, but there is some level of complication consideration that we need for that mechanism. So again, we'll cross that bridge when we get to it.